Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments. For tonight, we're going to take a look at modeling as a tool to make sense of the world around us. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI Technology to make tough-to-learn concepts accessible to all my students. Tonight, I'm super excited to be joined by our two panelists, Tom Dick and Gail Burrell. Tom is a senior math advisor for Texas Instruments and is also professor and former chair of the math department of Oregon State University. He has served on the editorial panels for the Journal for Research in Mathematics Education and the Mathematics Teacher Educator. He remains active in the College Board's AP Calculus program, and in 2008, Tom was inducted by the Oregon Council of Teachers of Mathematics into the Oregon Mathematics Education Hall of Fame. Tom, thanks for being with us tonight.
It's great to be here. Thanks, Mike.
And Gail was a secondary teacher in Milwaukee for over 28 years. Currently, Gail is a math specialist in the program for math education at Michigan State University. She served as president of NCTM and as director of the Mathematical Sciences Education Board. She received a Presidential Award for Excellence in Teaching Math and the NCTM Lifetime Achievement Award. Gail is currently a senior math advisor as well for Texas Instruments Education Technology. Gail, we're lucky to have you with us tonight.
Thanks for having us, Mike.
We're expecting a large crowd, so your audio is muted. Feel free to send any questions to Gail or Tom using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. As a reminder, the session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. We hope you don't have any audio issues, but in the event that you do, try toggling the audio broadcast on and off at the bottom of your screen. At this point, Gail is going to discuss our agenda.
So tonight, we're going to actually, you're doing the welcome and introductions right now. We're going to think just a bit about modeling with TI technology. Then we're going to investigate screening tests and herd immunity in some detail. And then we're just going to close with some resources for modeling.
Gail, thanks so much. And Tom is going to discuss our expected outcomes.
Okay, so tonight's actually our second webinar on modeling. We're going to focus especially on the use of it with disease frame. So we're hoping folks come out of this seeing the role of simulation in building understanding of mathematical and statistical concepts, recognize connection between what we teach and the mathematics related to the pandemic, understand terminology used to describe ideas related to the pandemic, and identify resources for integrating modeling into mathematics classes.
Thanks. I think this over to me. So
okay.
I'm going to share my screen, and hopefully I see my screen right now. I'm going to my PowerPoint. And as Tom said, is a session that we've done on modeling. We did one almost a year ago where we went through some of the other elements of this modeling. These activities can be found at the end. We'll show you where you can, but they're both in the 84 and in the Nspire, and you can find them on the resources on the education.technology.ti. So we want to look right now at some things that really have been in the news. So all these new ideas have cropped up. The idea of sensitivity, of transmission rate, herd immunity, false negatives, effectivity, efficiency of vaccines. So we thought it would be good to try to help find ways so that kids could understand what all of these words mean and what they might have to do with where we are in the world. So one of the things that we want to remember is that in the world, everything is variable. So there's all this variability that goes on. So we're going to actually start by looking at a sample of 500, where we know that about 20% of the population typically has flu. And we're going to look at what the screening tests can do. So here's just a class thing about looking about different kinds of samples that you might get when you are actually looking at samples from a 500 from a population, just to kind of give you a sense of what that is. So I'm going to do something that I've never done before. I'm going to try to do a simulation and have us fill in this table. And so I'm going to start by exiting here, going into my 84, and hoping that this all works right. And I'm going to open up the ProbSim app. If you guys have never used the ProbSim app, it's very worthwhile using. It's a great little app, and one that I used a lot before I actually ran into the Nspire. And by the way, we're going to do lots of things. If you have questions, be sure that you put them in the Q&A or even raise them in the chat. And at some point, we'll try and find ways to find out to respond to those questions. I'm going to put down here, and I'm going to use the marbles. You could choose different things. And I'm going to go to set, and I'm going to set this up. And I want to just run one trial, so that's good. And I want two types, so I'm going to have two types here. So I'm going to enter to set that up. And then I'm going to advanced, which is going to allow me to change my probability. So my very first thing is I'm looking at a set of 500 people, and 20% of them typically have the flu. So I want to know what percent will have the flu. So I'm going to say 1, and I'm going to enter. And then I'm going to go down here, and I'm going to say 4. And this will set up the 20% probably have the flu, 80% do not. And I'm going to say, okay. And I'm going to say, okay again. And now I'm going to say, yep, I want to do that. And it worked. And now I'm going to pick just one marble. And I got that marble was red. I'm going to pick 10 marbles. You can see each time I'm picking a marble, it changes. And I can see at the end of 10 marbles, I've actually really only picked one marble that was blue. So we want to speed this up a little bit. So we're going to do 20, 30, 40, 50. Oh, I see. And then we're going to go to 50, and we'll go all the way to a sample of 500. So we're looking at these 500 people, and we're trying to identify how many of them, don't let me go beyond this now, how many of them are likely to have the flu out of this sample that we looked at. So we've got the number 91. Okay, so now this is where it gets a little bit tricky. So I'm going to go back to my PowerPoint, and I'm going to look at this, and I have people with the flu. I have 91 people. So I'm going to enter that in my PowerPoint because I'm going to fill out a two-way table. If you guys have never used a two-way table before, it's a wonderful way to organize information that comes out of simulations, and especially when you're trying to do probabilities and conditional probabilities. So the total that had the flu was 91. So that means the total without the flu, I can actually fill that in, would be 409. I think I did that right. So now I'm going to go back, and I'm going to say, all right, I'm going to escape out of this. And I'm going to look at, and I'm going to escape all the way out, and it's yes. And now this time I want to go down, and I want to do my marbles again, but I want to set it up slightly different. I want to go to set, and I still want one. No, this time I don't want one trial. The number I got was, what was it, 91? Was that the number, Tom?
Yes.
91. So I'm looking at only the people that have the flu. Thanks, Tom. And now I'm going to go to advanced, and I have to change my probabilities here because I'm looking at now this vaccine for the flu, the screening test, it'll screen, its accuracy is about 75% accurate. So I'm going to enter 3 here, and I'm going to enter 1 down here. So that should give me a 75% accuracy rate for those people. So I'm going to say, okay, okay, yes. And now if I just click once to do my pick once, I look and I can see what I got. Out of those 91 people, 73 of them had the flu. So now what have I done here? I looked at the 91 people that were tested positive for the flu, that had the flu, and 73 of those 91 tested positive for the flu. The test was accurate, okay, for those. So now I'm going to go back to my PowerPoint, and I'm going to fill in those 73, and that would be right here. Those are the 73 out of the 91 that we had who tested positive for the flu. And that would mean this would be what, 18? Is that right? Not do very good arithmetic. Yeah, I think so. All right, so now I need one more little piece of information. I have to go back and start this thing all over again. So I'm going to escape. Yes, I want to go back to my marbles. There might be a faster way to reset this, but I don't really know what it is. And so I'm going to go back to set. And this time I have 409 that I want to look at. And you can do them one at a time or to watch it grow. But I figure right now we want to just get this done and look at what we've got. So I'm now going to go to advanced. And this time I want to have 1 here. And I'm going to have my 3 down here. Because I'm looking at those that didn't have the flu, and the probability that they would test positive should be 25% to be misdiagnosed here. So I'm going to do graph, and then I'm going to say good, and I'm going to say y equals. And now if I just click my pick in very quick short order, all of those without the flu, and it shows me that 92 of those without the flu tested positive. So now I'm going to go back to my PowerPoint, and I'm going to fill in those 92. So these are the 409 without the flu. 92 fills in here, and that leaves, let's see, 300 and what is it? 300 and
17.
17. Thank you, Tom. And he's probably ahead of me doing this arithmetic as well. So this would be 335, if I got that right. And that would be, this would be 165. Is that right? Mm-hmm. And so now I have my table that contains all the information that I'm going to need. And what I really want to know is that what about if I have a true positive? So we knew that this was about 75% accurate. So I can look at the number with the flu and positive, 73 out of 91. Okay, so I can fill that in, 73 out of 91. And I could calculate the percent. I might just actually go to my insert because I like that little quick calculator thing here. It was 93 out of 71. Some of you might be able to do this in your head. Oh, what did I do? Back. Okay. Come on. I just want the calculator scratch pad. All right. 93 out of 71. And that gives me, you're not doing this very well. 71 out of 93. Is that what I wanted?
I think you want to know the total, Gail.
Yeah. 93 out of, what was the total, Tom? Can you remember?
165.
165. See, he's so good. All right, so it gives me 56%. So I'm going to fill that in my table here, and that gives me about 56%. I'm taking a lot of time trying to set this up so you guys can really see the difference between this table and the next table. So I can do the same thing here with the false positives. So that's the number without the flu. The number without the flu would be these 409 who tested positive. So this is going to be 92 out of 409. Got any idea what this is, Tom, really quick?
Yeah, you know what, Gail, I think I might have messed up on your first one. So you're looking at the true positives, right?
Right.
So
the
that
number
73 over 91 was correct. I'm sorry, I was thinking it was you were after the row. So you did want the 73 over 91, which is going to be close to 80%.
This
The one above it.
Not close to 80?
That'll be close to 80. So you may want to go back to your calculator.
Okay. And the other one is 93 out of 409?
Right, which will be
93 out of 409. It's easier when you have a piece of paper and pencil in front of you, actually. 23% about?
right.
And so if I go back to my PowerPoint, I'm going to enter that in about 23% here. And what I've calculated here is a false positive. It's the number without the flu who tested positive out of the total number without the flu. And that's this 92 out of 409. Now I can calculate the false negative as well. So the number with the flu and negative. So the number with the flu and negative, I think could be 18. And out of the total number with the flu would be 91. Oops. And that's going to give me about, you got an estimate, Tom?
Yeah, it should be right around 20%.
20%. So we're just estimating here. And so this is what a false negative would be. And so basically, they're just reading the probabilities off of the table. And you have to think about what you really want to happen here. I don't think that's right. Is that really right? Okay. So basically, what we really want to do is we want to think about what these numbers mean in terms of the risk. So what's the potential consequence of a false negative? What if you test negative, but you really have the disease? Is that a good deal? You really don't want that to happen because you would be then thinking that you were not contagious and you'd be walking around spreading the disease. So in this case, a false negative would be not a good thing to have. In other cases, a false positive would be not a good thing to have. So it's something to consider. So I want to go back here and I want to see if I can actually pick up my whole table. This is pretty tricky here. And paste it down here. Worked. Because now I want to look at the conditional probability, the predictive probability, which is a whole different ballgame than a false negative or a false positive. Because here it's a conditional probability. I test positive. So given I test positive, that's out of 165. And the probability I have the virus if I test positive, so I have the virus, flu, tested positive, that's 73%. So that's the predictive value, 73 out of 165. And I can put Tom on the spot again. What does he think that is going to be about? I could go to my calculator.
I'm going to guess around 40%.
Around 40%? All right. And so that's the conditional probability. I can actually circle that. If I try to figure out how to make this go front and backwards, I guess I can't. It's not going to move for me. But I could put this around. This is the number that I'm looking at here. And then this is the total number that I'm looking at there. So I'm trying to figure out what is the actual probability that I have the virus given I test positive. I can figure out the same way the conditional probability, given I test negative, what's the probability I don't have the virus, and fill these numbers in. So I'm not going to do that. You can do that on your own, but this is helping kids, we hope, get a sense of what a screening test does. And this is predicated on a given prevalence with the test about 75% accurate. You can do the same thing on an Nspire. There's instructions on how to do that. But I'm gonna turn this over to Tom now, and he's gonna do an automated simulation.
Okay. Okay, so Gail's passing the ball over to me, and hopefully I'll be sharing a TI-Nspire screen with you. Okay, and Gail, maybe you can give me some feedback. Is that coming up okay?
Yeah.
Great.
Good.
Okay. So I just wanted to pick up kind of with a TI-Nspire version of some of the same things that Gail was doing. And Gail referred to an accuracy of the test being 75%, meaning if you had the flu, you were 75% likely to get a positive. If you didn't have the flu or you didn't have the disease, you were 75% probability of getting a negative result on your test. And occasionally, those probabilities are actually different for positive and negative. And so if your students, you may hear this in the news, they'll talk about the sensitivity of the test. That's referring to the true positive rate. So that's a probability you get a positive test result and you actually have the disease. And specificity refers to the true negative rate, meaning if you don't have the disease, this is the probability that you'll get a negative test result. Now, there are a lot of times when those two rates are really close to each other, and Gail, that's what Gail was working with was actually an equal sensitivity and specificity. They have 75% either way. But you can look at situations where tests vary in their sensitivity and specificity. This is just some vocabulary that's included in this file, but ultimately what Gail was looking at on her PowerPoint is this 2x2 table. And in the literature, some people call this a confusion matrix. And it's the rows here are positive tests. The second row is negative tests. And then the columns are whether or not you're infected with the disease or not. And this is where those categories of true positive, true negative, for example, if you have the disease and you test positive, that's a true positive. If you don't have the disease and you test negative, that's a true negative. And then these others are those false results. And the consequences of those are really, indicate, how serious a mistake those kinds of errors are. Okay? I think what Gail revealed was something I just find astounding and can be very counterintuitive. Think about what she said. She had a test that was 75% accurate, and yet if you tested positive, there was only a 40% chance that you actually had the disease, looking at that conditional probability. And that just blows my mind, and I think that's really surprising to people. And it can be, this happens when the prevalence of your disease is not real high. You can get those conditional probabilities can be really strikingly different than the probabilities of true positive, true negatives. So that's what we're going to take a look at here with the Nspire. So we've got kind of an automated sampling thing set up here. So I'm going to have a little trigger, slider that just triggers a new sample. And I'm going to be able to set how many people are in the sample of test cases. And then these are the parameters. We can set the prevalence. This is the percentage of people in the population that actually have the disease. And then the true positive rate and true negative rate is telling me how accurate my test is. Okay, so let's actually take a look. So let's go ahead and set some things here. I'm going to set the sample size at 100. That'll make it very easy to kind of calculate percentages. The prevalence, let's say there's only 5% of the people have the infection or the disease in the population. And like Gail, I'm going to set the accuracy being the same for both positive and negative results. So I'm going to set it at 90%. So we've got a really accurate test. It's 90% at detecting the disease, positive test. And it's also 90% accurate if you don't have the disease. It'll give you a negative result. Okay? And now what we have now is a matrix that will do this sampling for us repeatedly. And in fact, what we've got here, well, let me just go ahead. I'm going to draw a new sample of 100 people. And remember, there's 5% of the people have the disease. So that means only 5 people out of those 100. That was a nice sample. It actually came out to exactly 5 people. And notice that with that 90% accuracy for true positives, we didn't have a single infected person with a negative test. Okay, so we had no false negatives. Now, of the uninfected people, there's 95 of them. 3 of them tested positive. That's a really low percentage of these false positives. But look across this first row. If you had a positive test, there's only a 5 out of 8 chance that you actually have the disease, even though the test was 90% accurate. Let's draw some more samples. That's kind of a weird one. I guess that could happen. We just had nobody. That was lucky. Okay. Oh, here's a striking one. Okay, so 4 people had the disease. 3 out of 4 tested positive. 96 people did not have the disease. 9 out of those 96 tested positive. But what that means is that if you tested positive, there's only a 25% chance that you actually had the disease, which just blows my mind given a 90% accuracy. We can change the sample size, and we can draw repeated samples. So this is just a little TNS file, TI-Nspire file that kind of automates this sampling. You know, I will put a plug-in for kind of actually doing that sampling using some kind of random number generator, and Gail used the prob sim app on the 84 to actually draw out that simulation. One more page on this test simulation Nspire document with these same parameters that you can set. This is actually going to show the expected results. So if you did that sampling over and over and over again, what would be basically the expected results for many, many samples out? Okay. And so this would be one with a prevalence of the 5%, again, with those same accuracies for true positive and true negative rates. This is 2,000 people tested. You can see that the expected number, if 5% have the disease, that would be 100 out of the 2,000. And if we have 90% accuracy, that would mean 90 of those folks would test positive. But of the 1,900 people who don't have the disease, we would expect 190 of them to test positive. So again, it gives that kind of mind-blowing result. These become even more exacerbated if you raise the accuracy of your tests and you lower the prevalence, you can get some kind of really scary numbers, in the sense that if you tested positive, there might be a fairly low chance that you have the disease. Gail, I think I'm about ready to turn it back over to you, unless you have some comments.
I'm good.
Okay.
My comment actually would be, so when we started playing with this, we just really couldn't stop playing because the results were so intriguing, and they raised so many questions for us. And so if you think about different diseases like measles is really contagious. It has a really high prevalence rate. And then look at the tests that they have to screen for measles or some of the other ones. It's a really fascinating place to play around. And the activity on the website actually goes into some of those things. So I want to actually now look at the second problem that we cared about, and that is herd immunity. Okay. So herd immunity is, oh wait, before I do this, I just want to say one other thing. I want to reinforce what Tom said about the kind of hands-on activity that kind of went through it in a laborious way before you went to the next kind of automated simulation, before you go to the theoretical. I've read a lot of words and talk right now about people in stats classes going right straight to the theoretical, the expected values, but that kind of ignores the awesome variability that goes on. And so you can see the extremes, and some of them are very likely to occur. So it's important to stop and think about that variability that surrounds those expected values before you put all your faith in that expected value as the mathematical answer. It's kind of the difference between those who approach data from a mathematical perspective and those of us who think about it from a statistical perspective. So this next one is herd immunity. So that's a really big deal right now. Everybody's worried about how many people have to be vaccinated before we have herd immunity. And in herd immunity, there are two numbers that are important. One of them is the transmission number. How many people am I likely to affect if I actually have disease? And the other one, yes.
Sorry to interrupt. Would you like to share your screen? Because I don't think you are right now.
All right, thank you, Mike. I knew that I didn't do something. I have my screen up.
Thank you.
All right, good thing you're there. I said that before to keep us straight. Okay, so the two numbers are the transmission rate and the days contagious. And we're going to look just again at a small number of people, like maybe a nursing home with 100 people in it. And we're going to look at vaccinated or already immune, just 10% of this little population. So they either already had the disease or they received the vaccine. So I'm going to actually generate a population X, Y, and these populations are going to form ordered pairs, and so I can see a scatter plot of my population. And I'm doing this on a calculator page because if you do it on the spreadsheet or someplace else in the file, you might accidentally regenerate the random integers and change your population. So I'm going to put those two populations, X and Y, into my spreadsheet. I'm going to copy the first 10 rows and paste them into C and D and call them immune, okay? Because these are the people that were immune to start with. And then I'm going to actually make a graph. So I have set this graph up ahead of time with a window that will let me look at what the settings that will allow me to see the numbers that I generated. And I went down to -5 to give me a little bit of space so I can move things. And now I'm going to go and I'm going to insert my variable so I can actually see what this scatter plot looks like. So I have population X, going to go down and I'm going to insert my variable here, population Y. And that should give me a plot of all of the people that in our population. So those are our 100 people. And you have to be careful here. This is not, they're not actually geometrically spaced in terms of actual real position. It's just to give us a sense of how many people and what's happening to them. I'm also going to change the color, being fussy, because we do with several files and we want to have some kind of a consistent color so that the grayscale will always tell you what the original population is. I'm now going to go up and I'm going to add in my immune people. So I've generated those guys there. So I can add them into my graph by just adding them in. And I'm going to move them down and I'm going to change the color. I keep telling TI that red is not a good color. It should not be the very first option because too many people are colorblind. And so I'm going to make this magenta, which colorblind people can actually see. So now I can see this. So now the next thing is to say, all right, here's my community. Now I'm going to generate on a map notes page. I love the notes page. I'm going to generate a random number. So now remember, in my listen spreadsheets, I've got these rows and columns of 100 people that were on this scatter plot. So there's 100 people, and each one of those people is identified by a row number. So the person in row 92, and I can go to my spreadsheet and scroll down and look what that is. That person is infected, and that person is going to show up in my community right now, okay? And that person is going to infect 2 other people because my transmission rate is 2. So I'm going to click, and I've got person 92 infected the person in the 95th row, the 46th row. So I'm going to create here in a math box. I'm going to create something called infected, colon equals, and I'm just going to put 92 in it. That's my very first person. And then I'm going to, in another math box, I'm going to accumulate all my infected people. So I'm going to redefine, and the technology doesn't get much more complicated than this for this part. I'm going to augment infected with I. And so now that's the list of those people that are infected. So I'm going to go back to my listen spreadsheets now, and I'm going to go up here and I'm going to title a column infected, and you will see that the 3 people that were in my infected list on the notes page have now been put into this list and spreadsheets. And I need to know what the coordinates are so I can see who they are. So I'm going to title infect underscore X, and I'm going to title infect underscore Y. And I can actually go to my rows 92 and look up the ordered pairs, but I can also just go equals pop underscore X bracket, and I can say 92. And that will give me the X coordinate of the person in the 92nd row. I can do the same thing, equals pop underscore Y bracket 92, and I will get the ordered pair that goes for the person in the 92nd row. Repeating this, I can actually do this and pick up the coordinates for the person in the 95th row. Have to kind of pay attention here that I'm not doing something stupid, which I typically do, and the 46th row. And while you're doing this, you might, if inadvertently, randomly, you duplicate one of these, like this had been 95, you would skip it because you don't want to count that person twice. So equals pop underscore Y, oops, Y bracket 46. So now I have these 3 new people that are infected. So I'm going to go back to my graph, and now I'm going to add in my new 2 variables here. I have now got infected X, and go down, and I can add in my infected Y, and I now have a picture of my population the original population, the newly infected 3 people that are in this population. So now, basically, I'm going to continue this process. So these 2 people infected 2 new people each, the transmission rate, remember? So I'm changing this 2 to a 4. Now I've got these 4 more people. So my list of infected grew. So I added these 4 more people. Notice that these people were all distinct. If any one of them had been a repeat of one of the earlier ones, I wouldn't count that one. So these people are added in. I need to get their coordinates. So now I have 1, 2, 3, 4. I have 4 new. They're going to infect. I'm going to get 8. And I'm going to continue this process until I run out of random numbers, new random numbers. So I actually have done this over here. I continued that process, being very careful to keep track of who was infected and who newly got added, till I got these 6 random numbers. And they had every one of them had already been generated. So my newly infected people only ran into people who had already been infected. And that put me in this space right here. And so you can see these magenta ones are my original infected ones, and everybody recovers in 1 day, because that was what I set this up as to make it easy. And I'm going to look and say, these guys were all the ones that got infected. These were the immune. The ones that didn't get infected are my gray guys. If I count them, I have 30 little gray dots that never got infected. And so I have a herd immunity threshold of 70%. So by looking at how long the people randomly generated and ran into each other, it ended up with 30 out of 100 never got the disease. So 70% had to get the disease. And I think this took me like 14 days, something like that, in order to get to that point. So I'm going to stop sharing now, if I can remember how to do this quite right, and assign it over to Tom. And he's going to look at what this looks like when it's animated. So Tom, it's all yours.
Yeah. All right. So I hope everyone's seeing my TI-Nspire screen. And so I'm actually going to show this on both the TI-Nspire and the TI-84. By the way, the topic tonight has been part of this kind of larger effort Gail and I have been involved with, and trying to create some modeling activities as free resources for teachers that take advantage of TI technology. And so these TI-Nspire files and the TI-84 programs, along with the activities, are available on the TI website. So I encourage you, if they appeal to you, to take advantage of them there. So picking up where Gail worked through kind of actually creating the simulation. And now I want to look at working on this in a more kind of automated fashion, where we'll generate the simulation that way. So a couple
Can I interrupt you for 1 minute, Tom?
Sure, absolutely.
I don't want to really, he's on a roll, but I just want to be sure there's no questions in the chat, and I rattled on for a long time and Tom rattled on. Does anybody have any questions or observations before Tom tells you how this works on this part? Because we want to be sure to take care of any of those questions. So feel free to.
I forget to look at that, so I don't know if Mike has seen anything.
Yeah, so far I haven't seen any questions, just a couple of comments about how great the visuals are of what we've been doing recently.
Okay, so we didn't want to, we just wanted to be sure that there was places for you guys to ask questions, and if you have none, we'll let Tom go, and then you can be thinking of them, so we'll talk about them at the end. So sorry, Tom.
No worries. Okay. So what I've got here is a TI-Nspire file where you can set this transmission number that Gail was talking about. This is the number of people a contagious person would transmit the virus to each day. Keep in mind that if they transmit the virus to someone who's been vaccinated or who's someone who's already had the disease and recovered and is now immune, then that transmission won't result in a new person being infected. And then the other parameter here, this DC, that's the number of days an infected person is actually contagious with virus. Now I've set an actual, this is considered a pretty high transmission rate. If each person transmits the virus to 2 other people each day, that's pretty very contagious kind of virus. Kind of the cutoff that infectious disease people point to as a transmission rate of 1. So you want to get that number less than 1 if possible. So let's take a look at what this looks like. And I'm going to set my initial data numbers. I'll use the number 100 like Gail did. And I'm going to assume we've got 5 vaccinated people to begin with out of 100. And then of the remaining 95 people, 1 of them has the infection. So that's kind of my day 0 status. So 1 initial person infected, 5 people vaccinated, and then 94 are susceptible. So let me go ahead and set up those numbers, and then we're off to see a simulation. I can look at this just numerically. And so I can go through the days and watch these numbers change. And you can see that the uninfected is now, after just 5 days, there's only 21 people who are not infected. So this is really spread fast. And wow, so this is basically wiped out everybody. So everybody got the disease eventually in this scenario with that transmission rate. Now, just looking at the numbers may not be as compelling as a visual like what Gail had. So in this visual, the blue dots are vaccinated people. The gray dots are those that are uninfected but susceptible. And way up here, do you see that 1 black dot? That's that 1 infected person. And now I'm going to progress through the simulation again. Okay, I think we see now there's 3 contagious people, the original, and that person transmitted the disease to 2 others. And then when we get to day 3, you'll notice that original person now has finally recovered. They're no longer contagious. So we can progress through. And eventually, let's see what happens here. Wow. I'm not sure I see any, there's no more gray dots. Yeah, so that's what that transmission rate did. I'm going to set the transmission rate to 0.5. And by the way, this is something very important to talk with your students about. The number of days an infected person's contagious, that's a characteristic of the particular disease. But the transmission, and we can't really control that, but the transmission rate is something we can have an effect on through behavior. Social distancing, wearing masks, we actually can have an impact on that transmission rate. So, okay, so now I've set those new parameters. And let me go ahead and set this back to day 0. Okay, so this is the same situation, 5 people vaccinated, 1 person infected, but now we have a transmission rate of only 0.5. And notice that that transmission rate spreading more slowly. And this is interesting. We're actually, the disease now has died out. and notice that about half the people are escaped without being infected. So that transmission rate really had a profound effect on the spread of the disease. I think I'm going to switch over to the 84. Let's see, down here. And let's see, are you all seeing my 84 screen? Is that working, Gail? Okay, great. So this is the 84. Just wanted to show folks we have written a program. That lets us do a similar thing. Let's say we have 100 people susceptible, original number infected. Let's say we have 3 people infected, maybe 12 people vaccinated, and transmission rate, I'll put this one as 0.75. And the number of days an infected person, let's say it's just 2 days this time. And it's a similar picture to what we had before. And I'll just be able to hit enter. Okay, so the gray squares are the susceptible people. The infected ones are the black squares. The blue dots are vaccinated folks. That number won't change. And then the recovered people are black squares will turn magenta after they've gotten over their contagious period. So I'll just hit enter to go to the next day. Notice the number of infected people. So people are recovering. But the infected are starting to go up. Takes a little while to update each time. And so it's a similar picture for what we had on the TI-Nspire. Okay. I think I'm going to switch over to SIR real quickly, and then I know we'll need to turn it back over to Mike here in just a few minutes. So just want to give people a sense that we have this for both the 84 and the Nspire. Break out of the program and show you one other program we have. We also have a TI-Nspire file for this. This is SIR model, and SIR stands for susceptible, infected, recovered. That's what SIR stands for. Going to execute that program. And again, it says a number susceptible. I'm going to actually put in 1,000. Number infected, how about 10? And the number recovered, well, I'm going to actually say 0 to begin with, okay? And the transmission rate, well, let's go with 1. So each person infects another person once again. And then the contagious number of days, let's go with 3. That's the rate for, I think that's close to the rate for COVID. And then the number of days that we're going to plot the percent for, let's go ahead and do this for 40 days, see if that's enough. Okay. And what this now is, this is actually generating the simulation of the spread of the disease. The gray graph is our susceptible people. The black graph is our infected people. In fact, let me go ahead and turn on the trace. Okay, so we can trace, and by the way, the axis here, the vertical axis is percentage. So we should see that very close to 100%. Notice we only had 10 people out of 1,010 infected. So we can look at how the number of the percentage of susceptible people goes down. If we switch to the black graph, this is the percentage of people who are infected on any particular day. And then finally, the recovered people, oops, there we go, is the magenta graph. I'm going to go ahead and address something that was kind of in our PowerPoint, Gail, and that's that the pink graph, because the recovered people were formally infected, for you calculus fans out there, our black graph is in a sense giving us a derivative of the magenta graph. Or said another way, the magenta graph is in some sense an accumulation function for the black graph. What you think about why that makes sense. So I think I will stop there and turn this back over to Gail, maybe for some final comments, and back over to Mike. Or Gail, do you want to just say something here?
Okay, I was going to actually share my screen.
Okay, so let me assign that. I'll make you the presenter again.
Just for a minute here.
Okay, and I think I've made that pass back to you.
All right. So I just want to go back. Thanks, Tom. That was like way cool stuff. I want to go back just to a couple of things here on the PowerPoint. First of all, let's go back and think about the variability and think about this stuff that we're talking about right now fits in all sorts of your classes. It doesn't just have to be something extra. In statistics, you can talk about the variability. You can make sampling distributions. You can look at, what's a typical herd immunity threshold under given conditions. In the functions, just analyzing this SIR model. This is just susceptible, infected, and recovered. There's all sorts of questions that you can ask about how these functions behave and what's going on. It's a great thing to do because it's functions in the real world. And finally, in calculus, there's another whole set of questions you can ask. What about points of inflections? How are the graphs of the recovered and how are they related? You might even think about average value. There's a lot of calculus that's being involved in here. So don't think that this just has to be reserved for someplace special. And notice that the kids don't really need to know a lot of background math. They just need to make sense out of the math they're seeing. Also, I think it's important to go through this we even actually have hands-on activities to get them going, where they stand up and sit down in their class or on their virtual space right now. But the idea is to give them this progression so when they finally get to the automated part, where they can actually really start to investigate some interesting questions, that they can make sense out of what they're doing. Remember, this was making sense out of the world. So the TNS files were created by Tom, and he used a method based on Euler's formula for those of you who like calculus. And the theoretical background is from differential calculus, and that's the resource. Here's some resources that you might find interesting. We will make sure Mike has this PowerPoint because you can find the transmission rate for your state as of a certain date. You can also find the number of people who have had COVID per state. And I haven't done this right now because we're just coming up on this, but I suspect you can find a source that will tell you the number of people who've been vaccinated in your state. So this gives you another whole place to play with the things that you want your kids to explore that might make it more meaningful for you. So now I'm going to pass this back to Michael, and he can bring the whole thing to close. And thanks. Again, if you have any questions in the chat, or if you just want to email Tom and myself with any questions you might have, we'd be glad to answer them. Sorry we talked so much. This was a hard thing because it was an unfamiliar territory for most of you. Mike.
Thanks so much. I just want to share one thing real quick that I noticed whenever I was just moving through our website, education.ti.com. And this might be old news for Gail and Tom, but under activities, I just happened to look under Math Inspired, and there was a new option there that I didn't remember seeing before, and that's mathematical modeling. So I clicked on that, and there's some options there. So at least for Inspire, for what I just looked at real quick, I thought that was pretty neat to check out. So feel free to visit our website to learn a little more about all those activities that are free and available for your TI-84 or TI-Nspire. To receive a certificate of attendance for tonight, go ahead and click the link that appeared in the chat window. Also listed is a link for the documents tonight from Tom and Gail, including their PowerPoint. If you're watching this on demand, go and copy that link into your favorite browser to receive your certificate. Big thanks to Tom and Gail for sharing everything tonight. I know they spent a lot of time putting that together, and I think it's very appropriate for what we have going on in the world today to understand a little more about what these numbers are telling us. And I think it's pretty interesting to use things like probability simulator to try and make that happen. So thanks again so much, Tom and Gail, for everything tonight.
Thanks, Mike.
And
bye, everybody.
Thanks, Mike, and thanks everybody for being with us.
I agree. Thanks for joining us, everyone. We hope to see you back online next week. Stay safe and have a great night.